Hi, my name is Saket Kenjale, and in today's video, we're going to be continuing section 1.2, Basic Classes of Functions. And so we're first going to talk about behavior at infinity. So functions can go all the way to infinity or down to negative infinity, or they could stop at a finite number. So in this first red example, you could see that the function f of x is equal to x cubed goes all the way down to negative infinity as you go to negative infinity on the x-axis, and it goes all the way up to infinity as you go to infinity from the x-axis as well. And in this scenario, when it's f of x is equal to x over the square root of x squared plus 1, you can see that there's actually horizontal asymptotes where the function cannot actually pass these asymptotes, but as you go more as you go more to negative infinity, you are approaching negative 1, and as you are going more towards infinity, you are approaching 1. And now let's talk about quadratic and cubic behavior at infinity. So there's two types of quadratic shapes. So the first one is when the quadratic is facing upwards, and the other one is when it's facing downwards. So when it's facing upwards, you can see that when it goes to positive infinity, it's also approaching positive infinity from the y-axis, and when it's approaching negative infinity on the x-axis, it's also approaching infinity on the y-axis. But when it's a downward parabola, when you go to infinity, then it reaches negative infinity on the y-axis, and when you go to negative infinity on the x-axis, it goes towards negative infinity on the y-axis. And then for cubic functions, there are the cases of something like this, or something like that. And so in this situation, you can see that as you go to negative infinity, the y-axis also approaches negative infinity, and when you go to positive infinity on the x-axis, you go to positive infinity on the y-axis. And for this scenario, when you go to negative infinity, you actually go upwards to positive infinity on the y-axis, and when you go to infinity, you actually go down to negative infinity on the y-axis. Now we're going to take a look at zeros of polynomial functions. So when you're solving for the zero, you're finding where the graph intersects the x-axis. So zeros are also the same thing as x-intercepts. And you have to set f of x equal to 0 when you're solving for the zeros or the x-intercepts. So two common ways to solve for zeros is to either factor, and you're usually going to have to factor equation ax squared plus bx plus c, a quadratic equation, or you're going to have to use the quadratic formula to solve for the zeros. And you have to memorize this, so keep that in mind. Now we're going to look at this example problem. It says for the functions a and b, describe the behavior of f of x as x approaches, that means approaches, that arrow, so as x approaches positive or negative infinity, and find all the zeros. Then sketch the graphs of x. So, two things to keep in mind when graphing these functions is that, well, let's look at the first one. So the first two things you have to keep in mind is that one, it's a quadratic function, and two, it is downward facing because of the fact that there is a negative sign over here. And so when we graph this is a rough graph, by the way. When we graph this, we know that we originally went down 1 unit. So this was 1. This was the original graph. Well, a sketch of the original graph. And then it got flipped over the x-axis. So we're going to have something like this. It's going to be flipped over. So just by this we could tell the behavior of the graph. So we could say that as x approaches infinity, f of x, we say f of x approaches negative infinity, because as you go this way to infinity, the function goes all the way down to negative infinity. And then when you go to negative infinity, it also goes all the way down to negative infinity. So as x approaches negative infinity, f of x approaches negative infinity as well. So this is the behavior of f of x for problem A. And so now let's solve for these zeros. So we set f of x equal to 0, and it becomes 0 is equal to negative 2x squared plus 4x minus 1. And we can't factor this out, so we're going to have to use the quadratic formula. And it's going to be x is equal to negative b, so negative 4, plus or minus the square root of b squared, which is 16, minus 4. A is negative 2, and c is negative 1, all over 2a. And 2 times negative 2 is negative 4. Simplifying that out, we get x is equal to negative 4 plus or minus the square root of, so this becomes 16 minus 8, so it becomes square root of 8 over negative 4, and then that can become, the square root of 8 can become 2 root 2, because the square root of 8 is equal to the square root of 4 times the square root of 2, and then the square root of 4 becomes 2. And then we could factor out, and we will get the value of 2 plus or minus root 2 over 2. So these are our zeros, or x-intercepts. And so now let's draw an accurate graph of f of x for part A. So we know that so this will be 1, this will be 2. I won't label them though. And this is 1. I'll label that. And so when you use a calculator to find the decimal values of these, we will find out that one of them is equal to 1.707, and the other is equal to 0.293. So let's put that on the x-intercept. So we have 0.293 over there, and roughly 1.7 somewhere over there. And we also know that our vertex slash our highest point is at the point, was at the y value of 1. So now we have 3 points, and we can now draw a sketch of this graph like that. So this is it for part A, and now let's move on to part B. So I'm gonna rewrite this equation down here. So x cubed minus 3x squared minus 4x. Okay, so that is equal to f of x. And so some things we can know about this function is that when it's cubic, and the second thing is that it is a positive cubic, meaning that the graph is going to look something like this, or it's going to have the same shape as that. So now we could find the behavior of the function, and so we could see that as x approaches infinity, f of x approaches infinity, and as x approaches negative infinity, f of x also approaches negative infinity. So this is the behavior of this function. So I'm going to erase this and now solve for the zeros. So immediately I could see that all terms have an x in them, so I could factor out an x from each term, and also f of x equal to 0, so it becomes 0 is equal to x times x squared minus 3x minus 4. And now, simplifying this out, we get x, this is going to be x minus 4 and x plus 1. Yeah, that's correct. Okay. So now when you're solving for the zeros, we see that x is equal to 0, negative 1, and 4. So now when we're drawing an actual graph that looks similar to the actual graph, we have a 0, a negative 1, and a 4. And we also know that it starts out from the bottom, goes up like this, and if there's a 0 there, then it has to go back down, and then after that it has to go back up, whoops, and it has to go back up to this third 0, and it'll go all the way up like that. So this is a rough but almost accurate graph of f of x for part B. Let's look at mathematical models now. So mathematical models are real-world scenarios that can be described using graphs or tables. And so some examples of mathematical models include the study of population dynamics, investigations of weather patterns, and predictions of product sales. So let's take a look at this example over here. So it says a company is interested in predicting the amount of revenue it will receive depending on the price it charges for a particular item. The company arrives at the following quadratic function to model revenue R in thousands of dollars as a function of the price per item P. So this is their function. It is R of P is equal to negative 1.04 P to the power of 2 plus 26 P. And this is for the interval of 0 to 25, and including both of them. So A, they want us to predict the revenue when P is equal to $5 and when P is equal to $17. So let's do that. So let's write this function over here. R of P is equal to negative 1.04 P squared plus 26 P. So basically what question A is asking is they want us to solve for R of 5 and they want us to solve for R of 17. So let's do that. So it becomes negative 1.04 times 25, because that's 5 squared, plus 26 times 5, which is 30, plus 100, which is 130. And now I'm going to use a calculator for this. So negative 1.04 times 25 is negative 26. So the answer is 104. And so for R of 17, it will be negative 1.04 times 17 squared plus 26 times 17. And so that's equal to negative 300.56 plus plus 442. And then if you add those together, you get 141.44. And these are all in dollars, by the way. So that's the answer to part A. So I made a mistake because in the question it said that revenue is in thousands of dollars. We have to multiply our answers by 1,000. So the 104 that we had would become 104,000. And this value would be $141,440. So that is A. So now let's find the zeros of the function. So this is our function, and if we just factor a p out, we would get r of p is equal to 0. So we'll have 0 is equal to negative. So we could factor out p, like I said. So negative 1.04 p plus 26. Now we know that x is equal to 0, and p is equal to 0, and now we could set this equal to 0, and we'll find the second value of p. So it will become p is equal to negative 26 over negative 1.04, so that becomes positive. And then if I do that, we get 25. So the second value is 25. Now let's look at part C. It says to sketch the graph of R. And to sketch it accurately is going to be a little bit difficult because we do not know what the vertex of this parabola is. And so you might ask, how are we going to solve for, how are we going to graph this function? And the easy way to do it is that we got our zeros, 0 and 25, and so the midpoint is going to be the maximum of the parabola, and that is going to be our vertex. So the middle of 0 and 25 is 12.5. And so if we find the revenue value at when p is equal to 12.5, then we'll find the maximum value of the function. So let's do that. So it will be r of 12.5 is equal to negative 1.04 times 12.5 squared plus 26 times 12.5. And so when I simplify this out, it gets to negative 162.5 plus 325. And so that is equal to 162.5. And so now let's draw the graph. So in most real-world scenarios, you'll only need the first quadrant for your graphs. So I'm going to do that. And we know that our first x-intercept is at 0. and a second is at 25. And this value, by the way, is in thousands of dollars, but we're gonna keep it like that. And then so we could have 162.5 over here, and this is 12.5. This is the middle, and so our parabola is gonna look something like that. So this is the graph, and this answers part C. And then let's look at part D. Well, we solved it. So part D is determine the value of P that maximizes revenue, and so that value is going to be 12.5 because as you could see, 12.5 is what gets the most revenue, and this maximum value is 162.5, and it's in thousands of dollars, so the actual value would be $162,500. So this is the answer to part D. Now let's look at algebraic functions. So an algebraic function is a function that involves addition, subtraction, multiplication, division, rational powers, and or roots. So there's two types of algebraic functions, and first we have rational functions, and it's in the form of f of x is equal to p of x over q of x, where p of x and q of x are both polynomial functions. And then we have root functions, in the form of f of x is equal to x to the power of 1 over n, where n is a positive integer. So now let's look at this example problem 1.16. It says to find the domain and range for each of the following functions. So let's start with part A. So let's first look at solving for the domain. And we can see that if we put negative 2/5 in for x, we will get a undefined value. And so that's why the domain goes from negative infinity to negative 2/5, and then it goes from negative 2/5 all the way to infinity. For the range, it's a little bit more involved, but I'll walk you through it. So the best way to solve for the range is to isolate x, so let's do that. So what we could first do is set f of x equal to y. So we'll get the function y is equal to 3x minus 1 over 5x plus 2. And then let's multiply both sides by 5x plus 2. So that will cancel out. And then this will become 5xy plus 2y is equal to 3x minus 1. And then next, it would be best to subtract 5xy from both sides. So that would be 2y, and I'll also add 1 to both sides as well. 2y plus 1 is equal to 3x plus 5xy. So sorry, minus 5xy. Alright. So now we could factor out, sorry about that. Now we could factor out an x. So this will be like that. Then still 2y plus 1 over here. And then we divide both sides by 3 minus 5y. Sorry. So our final equation is x is equal to 2y plus 1 over 3 minus 5y. So now if we plug in a value and get an undefined value, then that's not included in our range, so we will take that out. And in this case, you could see that if we plug in a just a positive 3/5, then that won't work. So this won't work. So that is why the range will go from, I'll write this somewhere else. will go from negative infinity to 3/5, then from 3/5 to infinity. So those are our answers for part A. So now I'll solve for part B. I'm going to rewrite part B down here. So it's f of x is equal to the square root of 4 minus x squared. Okay, so let's first solve for the domain. And the best way to start is to notice that if you were to get a negative value out of this, then this function would not work. So we have to keep in mind that if we plug in an x value and it's 4 minus x squared, it has to be greater than 0, greater than or equal to 0. So we could say 4 minus x squared is greater than or equal to 0. And now we could solve for this inequality. So we could factor this expression out, and it could become 2 minus x and 2 plus x is greater than or equal to 0. And then we could separate them out. So 2 minus x is greater than or equal to 0, and 2 plus x is greater than or equal to 0. So this becomes 2 is greater than or equal to x, so x is less than or equal to 2, and then this would become x is greater than or equal to negative 2. So these are two separate inequalities, but we could combine them into this. So it would become negative 2 is less than or equal to x, which is less than or equal to 2. So this is our final inequality. And so this is written as an inequality, like I said, but if we wanted to write this in interval notation, then it would be bracket negative 2 to 2 close bracket. So that's the domain. To solve for the range, it would be best to solve it logically. So the range. So if we notice that we can only plug in these values into x to get a valid output, then using that information, we can notice that if we plug in a 0 into our function right here, so we plug in a 0, it becomes the square root of 4 minus 0, which is equal to the square root of 4, and that's just 2. This is going to be our greatest value. And if we were to plug in 2, then we will get the square root of 0, which is also equal to 0. And also, if we were to plug in a negative 2, we would get the same result. We will also get the square root of 0 or 0. So these are the lowest values. So according to that, our range would go from 0 to 2, and they are included in our range. Now let's take a look at transcendental functions. So transcendental functions are functions that cannot be described by basic algebraic operations. So examples of transcendental functions are trigonometric functions, exponential functions, and logarithmic functions. So these are some examples of trig functions. And then exponential functions are in the form f of x is equal to b to the power of x, and where b is greater than 0 and not equal to 1. And logarithmic functions, so they are in the form of f of x is equal to log base b times log base b x, and b is greater than 0 and not equal to 1. And it could also be written in the form like that. So those are transcendental functions. So now let's classify the functions as either algebraic or transcendental. So looking at this seems to be, looking at A, this seems to be an algebraic function because it has a root, and earlier we discussed that that was an algebraic function, part of an algebraic function, and this is a regular linear function. And this takes the shape of this, a rational function. So that is an algebraic function. Looking at this one, this seems to be an exponential function. So that's why this is transcendental. This is algebraic. And looking at this last one, this is a trig function, so it's obviously transcendental. Now let's take a look at piecewise defined functions. So just to know, for absolute value functions, this is the formula for absolute value piecewise functions. So f of x is equal to, and on the top we have negative x, where x is less than 0, and we have x, where x is greater than or equal to 0. So now let's solve this example problem. It says sketch a graph of the piecewise defined function. Okay, so let's first draw a graph. There we go. Like that. And so we could see that when x is less than 1, so everything on the left side of this, we have x plus 3 as our function. So let's draw that. So when x is equal to 1, y is going to be equal to 4. Oops, sorry about that. Y is going to be equal to 4, so it'll be 1, 2, 3, 4. Then when x is equal to 0, y will be 3, so it'll just be like that. It'll be a straight line, like that. So that's the first part. And so the second part is this. It's going to be x minus 2, and all of that is going to be squared. And that's when x is greater than or equal to 1. And so if we plug in 1 into this function, we will get 1 minus 2, which is negative 1. And that squared is equal to 1, just positive 1. So we'll have a 1 here. And by the way, to draw this more accurately, because 1 is not included in this, I didn't want to do that. Because 1 is not included in this, there should be an open circle right over here. And this is a closed circle. This is a closed circle because it's included with that equal to sign. So yeah, so this is equal to 1. And so for 2, it will be, looking at that would be 0. And for 3, that would be 1 again. So we have 3 points for our parabola. So let's draw this out. And I'll go something like that. So this is this piecewise function drawn out, sketched out. So yeah, cool. For our last page, we just have some transformations of functions, and so this is just a table which shows what transformations look like. So let's take a look at this last example problem for section 1.2, the basic classes of functions. So it says, for the functions below, sketch the graph by using a sequence of well-known functions. Let's first look at part A. So we know that the base function was originally an absolute value function, so it would be f of x is equal to the absolute value of x. And so now let's sketch a graph. And let's first draw a graph. Okay. And the absolute value function originally looked like this. Something like this at least. And so what was done to it is that it first moved left 2 units, then it was reflected over the x-axis, and finally it was moved down 3 units. Okay, so let's write that down. First, move 2 units left, then it reflected over the x-axis, and finally it's 3 units down. Okay, so let's follow this point over here is 0, 0, and then let's move from there. So first it moved 2 units to the left, so now this point is over here. Then it gets reflected over the x-axis. So originally it was like this, something like that, and now it's reflected over the x-axis, so it's going to look something like this. And then finally it moves 3 units down, so the final function is going to look something like this. Something like that. So that's it for A, and now let's move on to B. B, let me rewrite that. F of x is equal to 3 times root x plus, it's root negative x plus 1. So let's first draw a graph. Well, okay, so this was originally a regular square root function, and this goes something like this. So let's follow this point 0, 0 again, and let's see how it plays out. So first there was a reflection over the x-axis, on the y-axis, sorry. Then second, there is a vertical stretch, 3 units, and finally it moves up 1 unit up. So let's follow these instructions. So if it's reflected over the y-axis, then it's going to go something like this. Then there's a vertical stretch of 3 units. And when there's a vertical stretch, it usually goes higher up and goes around like that. So that would be the 3 that's going on. And then finally, it moves up 1 unit. So the final thing would be like this. Let's say this is 1. So it would start up here, and then I'll go up like that. That's pretty shaky. Let me read that. That would be what the final function looks like. So this is it for 1.2 basic classes of functions, and I hope you will join me in section 1.3 trigonometric functions. I'll see you there.